we got this integral from 0 to 1 log of 1 plus x times log of 1 minus x. Now, from first glance, there seems to be no good substitution or integration by parts that can solve this problem. But the moment we saw log of 1 plus x, that motivates us to use Taylor expansion, power series, and let's see if that can solve the problem. So first of all, first step, let's observe. The function seems to be even function when you replace x with negative x. So this turns into 1 minus x, this turns into 1 plus x, still the same thing. So to calculate the integral from 0 to 1, that's this area, which will be the same as this area. So this 0 to 1 area is half of negative 1 to 1 area. So all we have to do is times half from negative 1 to 1 log 1 plus x times log 1 minus x dx. That's all we have to do. But without this step, it's still doable. It's just a lot more complicated calculations in the end. Perhaps using some power series in the end. But this will make the calculation a little bit easier. So now we make substitution. We let 1 plus x equal to t, for example. So x is equal to t minus 1. We change the boundaries, of course. I equal to half of, when x is equal to negative 1, x is equal to negative 1, t is equal to 0. When x is equal to 1, t is equal to 2. We have log 1 plus x becomes t times log 1 minus x, 1 minus this part. All right, so 2 minus t, in fact, dt. Right? So from here, we can easily just extract 2 out of here. All right, so by extracting 2, we have log 2 times 1 minus half t. Right? Then we can just say, okay, split this logarithm. Log t times, first of all, log 2 plus the other log 1 minus half t dt. So again, split it into 2 integrals. Log 2, of course, is a constant. Half log 2, 0 to 2, log t dt, plus half (0 to 2) log t times log. So here, perhaps I'll make change of half t becomes y. Okay, so here we change the boundaries here. Right? When t is equal to 0, y is equal to 0. T is equal to 2, y is equal to 1. So from 0 to 1. dt, right? Half t is y, t is 2y. dt is 2 dy. So 2 times half, gone. Just 1. Then we can use dy. Right? Because t becomes 2y. In the end, we have dy. Here we have 1 minus y. Right, that's the second integral. And as with regard to this one, standard integral by parts. Right? So without getting into details, I'm just going to write down the results. Half log 2 times this integral is in fact 2 log 2 minus 2. Right, just standard integral. So this part, again, we break it, we split this logarithm, log 2 plus log y. Okay? Log 2 plus log y and log 1 minus y dy. Okay, so that is in fact log 2 square minus log 2. Okay. Again, likewise, we multiply this to that. Okay, log 2 is a constant again, plus log 2 0 to 1 log 1 minus y dy. We multiply this to that, plus 0 to 1 log y times log 1 minus y dy. So again, this part, right, standard integral by parts, right? Just easily, just quickly, log 2 squared minus log 2. So this is in fact negative 1. So negative log 2 combined with this, negative 2 log 2. Right? Then we copy down this, 0 to 1. Log y times log 1 minus y dy. So all we have to do is work out this integral. Like I said from the beginning, our main motivation is to use the Taylor power series of log. So in the end, we reached this result. Like I think all we have to do is to work out this one. Now, knowing that power series of log 1 plus y minus half of y squared plus 1/3 of y cubed minus, right? Plus minus plus minus plus. So like, of course, y is in negative 1 to 1, including 1. So following this immediately we have, if it's 1 minus y, then immediately we have replace y with negative y. Minus y minus half of y squared. Next, still minus. Every term is minus. So let me just take out the minus. Rewrite it into n goes from 1 to infinity, n at the bottom, y to the power of n. So here, of course, y is from negative 1 to 1, including negative 1. Right? That's its, where it's meaningful. It's a convergence radius of the power series. So, if we just, then we can multiply log y into this infinite sum, right? That's perfectly okay. All right, so let's just call it I naught, right? So I naught is equal 0 to 1. Let's take out the negative. All right, there is negative. So n goes from 1 to infinity. And like I said, multiply log y into it. Y to the power of n times log y. Right, then we do the integral. Right, first we do the sum, then we do the integral. Now the question becomes, can we switch the order of infinite sum and integration? Right, so long story short, it is perfectly legal in this case. It has something to do with the uniform convergence of the improper integral. Improper integral. So it's kind of like a generalized case of if it's proper Riemann integral, right? Then we have uniform convergence, so then we can have the conclusion. But this is also okay. You can find the conclusion in some textbooks. Some textbooks include this in main text. Some other textbooks put it in exercise questions, but that's the conclusion. I switch the order. Negative. Right, outside. First, let's do integration. Right. Log y. Then we do infinite sum. Right? Integration is simple. Standard integral by parts. Right? Just through one step, we can easily reach the conclusion that it is equal to, the n has nothing, so n stays. And the rest of the integral is negative 1 over n plus 1 square. Right? Negative becomes positive. So in the end, we have this. Right? So all we have to do is, of course, split the partial fraction. That's standard. I'm just going to skip the steps. So straight away we reach this 1 over n minus 1 over n plus 1 minus 1 over n plus 1 square. Right, that's the final result of a partial fraction. So now we easily just split the sum. Easy to split. Minus. So this sum n goes from 1. Right? So the bottom goes from 2. So n goes from 2, 1 over n. Change it into n, right, to infinity. This minus, again, the bottom goes from 2 square. Right? Just change it into n square, then n goes from 2. Right? So the majority of the terms cancel out, right? That goes from 1. Only the first term stays, right? The rest cancel out. So first term 1, this term, right? If we go from 1, we have the well-known pi square over 6. But now we don't have 1, so still minus, right? We plus 1 minus 1, right? Plus 1 minus 1, plus 1. We give the 1 to this. So this becomes pi square over 6. Right, still the same thing. So 2 minus pi square over 6. Right, that's the I naught, like I said. Right, I naught. So the entire integral equal. Right, the entire integral equal this part plus this part.